Today we are moving to a different topic. Our discussion so far was on instruction set architecture, and now we will start discussing about microarchitecture, which means how instructions which we have studied so far, how they are realized in hardware. So, we will begin by looking at how basic operations are done in hardware. We will talk of arithmetic operators, logical comparison and so on, and eventually we will see how a heart of the processor called ALU or arithmetic logic unit is built. So, we have so far seen what instructions are, what is their usefulness, what is the purpose of each instruction, and what is the functionality they achieve. We have also talked about how performance is defined, and to some extent we have seen the relationship between performance and instructions. So, when we continue with this, we develop an understanding of microarchitecture and relationship between instruction set architecture and microarchitecture, and idea of performance will be even more clearer. So, essentially what we are aiming at is designing something like this, an ALU, which typically works on 2 operands. In our case, for MIPS processor, these will be 32-bit operands, and produces a result under control of some signals which are determined from the instruction. So, depending upon which instruction you are trying to execute, this unit will perform some operation. It might perform addition, subtraction, multiplication, division, or do some comparison, or do some logical operation. Okay. So, in next few lectures the focus would be design of this. So, talking of this topic, this is the sequence of subtopics we will look at. Starting today I will talk about binary arithmetic and design of ALU in a very simple situation. Then I will try to include idea of overflow. Okay, when result exceeds the limit, what do we do? We will separately talk of multiplier and divider design, which are more complex operation than simple add, subtract, and or. We will look at some techniques to speed up the key operation of addition or subtraction. Then we will move on to non-integer operations, floating point, how such numbers are represented, and what kind of operations are performed over these, and finally the hardware to carry out these operations. So, today in particular, starting with binary representation, we will see how addition and subtraction are done and how the circuit is built. We will talk of comparison a little bit, logical operations, and finally come up with the ALU design for some of the MIPS instructions. Okay. I presume that you are familiar with binary representation to some extent. We will just refresh it so that you are comfortable and you can quickly follow what we discuss later on. So, as you know, inside computers everything is represented in bits. Okay. Each bit represents 2 states 0 1, and there is no inherent meaning assigned to a bit. A bit could represent different things. Okay. It depends upon the context in which you are looking at a string of bits. It could represent an integer, could represent a fractional number, it could represent a piece of text, it could represent some logical value or some symbols in an encoded form. So, the context in which you look at set of bits decides what actually they mean. So, you have to interpret them in one of the many different ways depending upon when and in what circumstances you are looking at those. So, to begin with, let us talk of integers represented as strings of bits. So, essentially from mathematical point of view, we are talking of binary numbers which are essentially with radix 2 or base 2. So, a string of n bits can represent a number which will correspond to a number in the range 0 to 2 raised to power n minus 1, okay, because with n bits you can represent 2 raised to power n patterns you get a range of numbers 0 to 2 raised to power n minus 1 if you are considering only positive numbers or non-zero number, I should say. So, but with this simple idea we need to talk of a few more complications. For example, in mathematics you talk of integers ranging from minus infinity to plus infinity. Okay. Here we are talking of a finite range. So, it is not a strict one-to-one correspondence between integers as we understand in mathematics and integers we are trying to represent here. So, there is a question of overflow which we are going to discuss later. We also have to worry about sign of the numbers, how to represent positive and negative numbers. Number of choices exist and we should understand the implications of those choices. How do you represent fractions? Okay. So, that makes things little more complex than simply looking at a string of n bits as a pattern representing numbers from 0 to 2 raised to power n minus 1. Okay. So, starting with negative numbers, there are several representations, particularly 3 which have been used commonly. One is called sign magnitude, where if you have n bits, you keep 1 bit for the sign and remaining n minus 1 to represent magnitude of the number. So, the first bit typically would represent a sign, typically 0 corresponds to a positive sign and 1 corresponds to negative sign. So, in a 3 bit situation, these 8 patterns would correspond to the integers shown here. Okay. So, the magnitude can range obviously from 0 to 3 with 2 bits kept for the magnitude, and therefore, the range is 0 to 3 on positive side and minus 0 to minus 3 on the negative side. Interestingly, you would notice that there is a plus 0 and minus 0, of course, which mathematically mean the same thing, but all the same 0 magnitude can be prefixed with a positive or negative sign, and there are 2 representations of the same number. 1's complement is a notation which says that if number is positive, you represent as if you were handling a positive number ordinary without any change, but if it is negative, then you flip all the bits, okay, turn zeros to ones and ones to zeros. So, if you take 0 0 1 for example, which represents plus 1, you make it 1 1 0 like this, it becomes minus 1. Okay. So, once again the range of number you can have is same, 0 to 3 on positive side and minus 0 to minus 3. Once again 0 gets 2 representations. The third column here shows what is called 2's complement representation. Here positive numbers coincide with what you have seen in other cases. Okay. The representation of positive numbers are identical in all cases, but negative numbers here are with a 1 offset from this. So, for example, the largest number which you see here is minus 3, but here we get minus 4. Okay. Minus 2 becomes minus 3, minus 1 becomes minus 2, and minus 0 we have gotten rid of, that is minus 1. Okay. So, essentially this representation removes this ambiguity. Each number has a unique representation. So, that is a plus point we are getting, although the negative point seems to be that the range is unbalanced, right. Range is unbalanced in the sense that on the negative side you can go up to minus 4, but on the positive side you can go up to plus 3. So, in general whatever be the number of bits, the range on negative side will be 1 more than what you have on the positive side. So, that is the so to say a negative point of this representation, but more significantly an important positive feature here is that it actually eases the arithmetic operations and makes the hardware somewhat simpler. Okay. Now, what is the definition of this representation? this is basically for negative numbers, it is in magnitude 1 more than 1's complement. Okay, 1's complement is defined as flipping all the bits, and if you let us say if you take say a number like -2, okay, so its 1's complement is 101 obtained by inverting all the bits, and if you add 1 to that, you get 110, you get -2. So, 1's complement plus 1. This shows the range of number you will get in a 32-bit word as we have in MIPS, and following 2's complement representation. So, all zeros is 0. On the right side I am writing their equivalent values in decimal base 10. Okay. So, this is 0, then 1, 2 and so on. The largest number is 0 followed by all 1, that is the largest positive number, and it corresponds to 2 raised to the power 33, 2 raised to the power 31 minus 1. Okay. This 31 is 1 less than the number of bits you have. The smallest negative number is all 1's. So, basically if you take 1's complement of plus 1, you will get all 1's with a 0 at the end, and you add 1 to get this. Okay. So, this represents -1, and as you go this way, the magnitude is increasing. The largest negative number you will get is 1 followed by all zeros, okay, and it is minus 2 raised to the power 31. Right. So, these two numbers are max int, maximum positive integer value, and min int, which is the most negative integer value. So, approximately 2 raised to the power 31 would be about close to over 2 million, over 2 billion, sorry. Okay. All right. How do you perform addition and subtraction with binary numbers? Again, I presume some familiarity, so I will go over this quickly. Basically, the method is, there is nothing new in the method. You add or subtract exactly the way you do with paper and pencil, as you learnt in school. Only thing you have to represent, only thing you have to remember is that numbers are in base 2. Okay. So, when you add 1 and 1, for example, you get a 0 and a carry, right. So, let us look at a few examples. This is adding positive 3 and positive 2, adding 5, subtracting 2 from 5, subtracting 5 from 6. So, you get 5 in first case, and as you would expect 3 in the second case. Of course, now this is showing as if bits are generated from left to right, but when you work it out, you actually have to work from right to left, because carry or borrow will flow from right to left. Okay. Now, I took these examples carefully, so that the result is within the range which is permissible by 4 bits we are having at hand. Okay. What happens when the number is larger than what the word can accommodate, that we will discuss later. Okay. Now, if you bring in the sign, if you bring in negative numbers, what we did was adding and subtracting positive numbers. If you have negative numbers and you are representing in 2's complement form, then again it does not complicate the life at all. Okay. So, when you are adding or subtracting, you continue to think of them as positive integers. Okay, do not worry about the fact that they are sign 2's complement number. Perform addition or subtraction as you would do without sign, and if your result is within the range, then you would have got correct answer. Okay. So, the key is that you perform add or subtract operation ignoring the sign. So, here are a few examples. So, we are trying to do 7 minus 2, we expect basically we are adding minus 2 to 7. Okay. So, we should get an answer 5, and there is a subtraction of minus 2 from 5. So, you should get plus 7 as the answer. Subtracting 5 from 2 should give a negative answer, which is expected to be minus 3, right. So, just quickly make sure that these representation, these numbers which I have written are correct. This is representation of minus 2. Okay. You can do either way. If you want to find out what is the representation of minus 2, you could take positive 2, take one's complement and add. Okay. If you are given a negative number like this and you want to find out what it represents, again do the same thing. So, take its one's complement, okay, or invert all bits and add 1. So, if you complement this, you will get 0, triple 0 and 1, and you add 1, you get 2. So, basically this is a representation of minus 2, and you would notice that you get correctly plus 5 when you perform addition. All right. I have added just without knowing that it is negative or positive. You simply add as if these are positive numbers. If there is a carry going out, just ignore it, right. If the result is within the range, then you will get correct answer. So, same thing is happening here, although there is a carry flowing out. Okay, we have just thrown it. What you are getting here is plus 7 as we expected. In this case, let us do it step by step. So, you subtract 0 1 0 1 from 0 0 1 0. So, here you get a 1, there is a borrow that eats away this 1. So, you get a 0, here again there is a borrow, you get a 1, there is again a borrow, you get a 1 here. Okay. So, now there is a ultimately a borrow from the left side, which again like carry we are neglecting. So, you have here 1 1 0 1. What does this represent? You find its complement 0 0 1 0 and add 1 to it. So, you will get 0 0 1 1, which is 3. Okay. So, this is representation of minus 3. Okay. So, these examples just illustrate the point which I mentioned earlier. Question is why does it happen? Why is it you are able to ignore the fact that it is sign? The answer lies in the fact that a 2's complement representation is actually nothing but 2 raised to power n minus x. So, if you are trying to represent minus x, let us say x is the magnitude of a number and you are talking about minus x, a negative number with magnitude x. So, its 2's complement representation is nothing but 2 raised to power n minus x. Okay. So, you take this large positive number, x will always be less than 2n. Okay. So, this positive number minus this positive number could be thought of as a positive number. So, if you had unsigned number system, right, representation of this positive number in that is what you are representing minus x as. Okay. So, let us look at some example. Suppose we want to see how we represent minus 3. So, it is 2 raised to power 4. Okay. We are talking of 4 bits. So, of course, 2 raised to power 4 is a 5-bit number, but it is just something we are doing on paper and pencil. Out of this you subtract 0 0 1 0 and what you get is 1 1 0 1. Okay. So, this is same as complementing these bits getting 1 1 0 0 and adding 1, okay. Because going back to this one, 2 raised to power n can be written as 2 raised to power n minus 1 plus 1, okay. So 2 raised to power n minus 1 is let me write it here. Okay. So 2 raised to power n minus 1 is all ones, okay. So you subtract a binary number from all ones, basically each bit will get flipped, right, and then you are adding a 1 later on. So this just shows the relationship between two ways of looking at it. So now what we are doing when we are adding and subtracting 2's complement number is that minus negative numbers are bringing additional 2 raised to power n into the picture. So suppose, in fact, so if you have several numbers x, y, z, w, 4 numbers to be added, some of them are negative, okay. So with the negative number we are carrying an extra 2 raised to power n, okay. So if you are adding a series of numbers, some positive, some negative, we would be carrying a few extra 2 raised to power n's, which will all go out as superfluous carry on the left side, okay, and the result we get is a correct value. Okay, now this representation, this way of relating negative numbers to their representation brings us to an easy way of doing subtraction. Suppose you want to carry subtraction of x and y, you want to do x minus y, y you can look upon as 1's complement of y, and sorry, minus y can be looked upon as 1's complement of y together with a 1, okay, right. So basically this subtraction can be looked upon as addition of x and minus y, and minus y is this, right. Okay, there is one additional factor you need to keep in mind is that there are some instructions, for example add immediate, which require one operand to be 16 bits and one is 32 bits. So how do we perform addition or subtraction with one large integer, one small integer? The hardware which is there inside the processor would be common for add instruction or add immediate instruction, okay. The addition is, adder is capable of adding two 32 bit numbers. So basically what is done is the shorter integers, 16 bit integers, are actually re-represented in 32 bits, okay. So how do you do this conversion? The most significant bit, which is actually the sign bit, is repeated to fill up those additional 16 places, okay. So if you have positive numbers like 0 0 1 0 in 4 bits, in 8 bits they get represented as 4 zeros followed by 0 0 1 0. But if you have negative numbers, it is this 1 which will get extended, okay, 1 1 1 1, then 1 0 1 0, right, okay. Because this, for example, this what is this number? Its 1's complement is 0 1 0 1, which is 5, and if we add 1 you get 6. So it is minus 6. Now minus 6 when represented as a 4 bit negative number gets us this. If same minus 6 we had represented as 8 bit negative number, we would have got all these positions filled with ones, okay. So in simple terms, we look upon this conversion as a sign extension. The sign bit is extended to fill up the additional bit spaces which you have. Okay. So, now because of this, some instructions like load byte, which are only filling up part of the word, we have talked about load word, which gets one word or 4 bytes from memory and fills up a register. There is also an instruction load byte, there is also one load half word. So, load byte picks up 1 byte from memory and places in a register. Now, the question is what happens to remaining 3 byte positions or remaining 24 bits of the register. In if you are looking upon this byte as a signed byte, then they should be filled up with the sign. If you are looking at this as an unsigned byte, they get filled up with sign bit. So, there are actually two different instructions, load byte and load byte unsigned, LBU. So, LBU will fill up the remaining 24 bits with zeros, LB fills with the sign of the byte which you got. Okay. So, bit number, if you are numbering from 0 to 31, bit number 7, which is a sign bit, replicates and fills up all the positions. Okay. Now, let us move towards a circuit design for performing addition. The method is, simplest method is to follow what we do on paper and pencil. Okay. Basically, we move from right to left and perform addition bit by bit. So, if you know how to perform addition of 1 bit, that means at 1 bit position adding 2 bits and also carry coming from right side, you can just repeat the same thing for 32 bits. So, each bit, let us say we are talking of ith bit of 2 operands A and B. So, AI and BI represent the ith bit of 2 numbers A and B, SI represents ith bit of the sum, CI represents the carry coming into this position from right side, and CI plus 1 is the carry going to the left side. Okay. So, this is a unit, this is a module which performs 1 bit addition, and a circuit to add two 32 bit numbers is nothing but a cascade or an array of 32 such units, right. So, the carry signals are those which connect one unit to the other unit and form a chain. Okay. Initial value of course is 0, which is the initial carry for bit number 0. So, I am assuming that bit 0 is the least significant bit and bit 31 is the most significant bit. So, now following 2's complement notation, I do not need to worry whether A and B are signed number or unsigned numbers, whichever they are, I simply pass them through a circuit like this, which to begin with is designed for unsigned numbers. Okay. Now, what is this 1 bit adder module? It can be designed by trying to look at various possible inputs it has to cater for. So, which can be listed in the form of a truth table. This truth table defines row by row what happens for each combination of inputs. Okay. So, we have these columns labeled by the inputs AI, BI and CI, and here are 2 columns labeled by the outputs CI plus 1 and SI. So, we have these 3 inputs and 8 different combinations which you can form for these 3 inputs, okay, 0 0 0, 0 0 1 and so on, and finally 1 1 1. For each of these we need to exhaustively define what the outputs are. Okay. So, what we can do is we can find out how many ones are there. Okay. If this is a case when there is no 1, so both sum and carry are 0. In this case and in this case, this and this, these are 3 cases where you have a single 1. So, sum is 1 and carry is 0, like this or like this, these 3. Okay. Then there are some cases where you have two ones. For example, this. Oops. Here you have two ones. Here you have two ones. Here you have two ones. So basically, two ones make it equivalent of binary 2, which means sum is 0 and there is a carry. Okay. Same way here, same way here. And this is a unique case where you have all three ones, which means number 3, sum is 0, sum is 1, carry is also 1. Right. Now this describes the relationship between input and output, and which can be captured by Boolean equations, and Boolean equations then define what circuit you require to implement this. So as far as sum is concerned, it is those 4 combinations of A, Ai, Bi and Ci where we had sum as 1. So this one where you have a single one, a single one, a single one, and all 3 ones. Or another way of looking at this is an exclusive OR of Ai, Bi and Ci, which means that if number of ones in is odd, you have a 1. If number of ones is even, you have a 0 here. Okay. Carry on the other hand is 1 when you have 2 or more inputs as 1. So either they could be Ai and Bi, Ai or Ci and Bi, or these two or these two or these two. Okay. The case of all 3 being ones is actually covered by this. You can actually, if you are familiar with Carnot map, if you have done this in your digital electronics or you might be doing it, you would know how to get this systematically by drawing a Carnot map and finding a minimal representation in a sum of product form. So now once you have got Boolean expressions representing the output, you can straight away come up with circuit design which will do this. So you have AND gates and OR gates, you connect them exactly as dictated by this to get the design. So I will not go into that. One thing which I like to point out here is that the number of possibilities is large. There could be several ways of writing these Boolean equations, and therefore you can have different circuits. So for example, in case of sum I showed 2, and there are many more ways of representing depending upon which gates you want to use, and there are also variations in different representations in terms of whether you have 2 input gates or 3 input gates. If you have term like A, B, C, that means you are talking of AND of 3. Okay. So question is you want to work with 2 input gates or 2 input and 3 input gates, or whatever your choices are. Okay. What is the fan in of a gate you want to limit to? The other issue may be that you have stages of logic, and or representation means that you have two stage logic. Okay. You have AND terms formed by AND gates, and then you are ORing all those. So more stages, more gates a signal has to go through, more would be the delay. Okay. So implication of all these choices is different speeds, different costs, maybe different power consumption. Okay. So that itself is a more complex issue, which in course like digital hardware design you will see it more closely, more deeply. Okay. So for our purpose, we will often try to use circuits which are easy to comprehend, easy to arrive at and comprehend. Okay. Okay. Now we have seen how to build an adder. How do we build a subtractor? So basically we are going to use this formula, that x minus y can be represented as an addition of x and y's complement, and then you can add one more. So now please note that x and y themselves could be signed numbers. Okay. This formula is not just for x and y as 2 positive integers. X could be positive or negative, y could be positive or negative. Okay. So this will hold. So to get 1's complement of y, you simply need to put inverter for the second operand. So, now we had A and B as our operands. So, Bi is inverted before making it as input to the adder, right. So, that takes care of doing x plus y prime, or adding 1's complement of y to x. And when you put these modules together to form a 32-bit subtractor, this plus 1 can be taken care by making the initial carry as 1, which is normally 0 in case of an addition. Okay. So, these are the two changes. Each B bit is inverted and the carry is initial carry is made 1, right. Now, with these two circuits for adder and subtractor, we can see easily that they can be combined. Okay, there is a slight difference. We can combine and come up with a single circuit by using a multiplexer. What multiplexer does, it selects one of the many inputs it has. Okay. So, in our case the choice is between taking the Bi bits directly or through the inverter. If we can put multiplexer to choose one of those two, then we have a single circuit which will do addition or subtraction depending upon how we control the multiplexer. So, we have the same adder, the Bi input can go either directly or through the inverter, okay, and this multiplexer is choosing this, right. It requires a control signal or an control input, which we are calling as BINV, standing for whether B should be inverted or not. So, it is controlling. If you give a 0 here, the multiplexer will select this input which is labeled with 0, and the circuit will do addition. If you put it as 1, then this inverted input will be taken and circuit will do subtraction. So, putting these boxes, okay, I am not showing the details now. Each of these blue boxes is repeated here. Okay, I am calling it adder or subtractor. The carry input also needs to be controlled, and it so turns out you can use the same signal BINV. So, when BINV, this control signal is 0, the initial carry is 0 and the bits of number B go without inversion. When this input is 1, initial carry becomes 1 and bits of B, B0, B1 etc. go via inverter. Okay. So, this control signal is going to all these modules. All right. Now, these are two arithmetic operations. We have seen their implementation. We have not looked at multiply and divide yet. Let us move towards logical operations and OR. Okay. So, now the instruction which we have in MIPS, AND instruction and OR instruction, what they do is they perform logical operation bit by bit on 32-bit vectors. So, for example, if you have one register containing this, another register containing this, and you perform AND operation, you will get this. Okay. All that we have done is that we have performed bit by bit AND operation. So, only when both are 1 you get a 1, otherwise you have 0. Similarly, OR operation over the same two numbers will give you this. Wherever you have either of them being 1, you get a 1, and only when both are 0 you get a 0. Okay. So, the circuit for doing this is very simple. There is no relationship between what you are doing for bit I and what you are doing for bit j. So, for each bit position you have an AND gate, right. So, ith AND gate ANDs AI and BI to give you SI. Similarly, ith OR gate out of 32 OR gates ORs AI and BI and gives you SI, which is OR of these two. So, now let us combine all these four. We have addition, subtraction, ANDing and ORing. These 4 operations could be combined, and let us try to construct a very simple ALU. We would need to enhance it further to bring in more operations, but let us keep this as the present target. And once again, all you need to do is put various things together and add a multiplexer. So, this multiplexer has now 3 inputs, which I have labeled as 0, 1 and 2, and depending upon a control input which is labeled as operation, either we will select this or we will select this or select this. Okay. So, the input AI and BI are spread out to all these 3 components, okay, to add AND circuit, to OR circuit, and to this adder cum subtractor. Of course, for purpose of subtraction, we are actually having this BI routed through this inverter and multiplexer. Okay. So, this is one module or one bit unit of ALU, which is capable of performing one of the 4 operations, and it needs to be guided by this input, which can have 3 possible values, and this input which can have 2 possible values. Of course, this is ignored, or it is do not care when you are performing AND and OR operation. Okay. So, when you are actually choosing this or this, what you are doing here does not matter. Okay. So, this part basically effectively what we are doing is the circuit is always there for performing all the operations, right. So, you give some AI and BI, and the circuit would do AND operation as well as OR operation, and one of the 2 among addition and subtraction, but you are picking up only one of the results, right. So, when you are doing AND operation, for example, this whether it does addition or subtraction does not matter. Okay. So, therefore, the value of this is ignored when this says you pick up 0 or pick up 1. It is significant only when you are picking up 2 here. Okay. Now, here is a cascade of 32 of such units, which are called ALU 0, ALU 1 and so on up to ALU 31. So, you notice that on one hand we have this B inverter going to all of them, and particularly in the first unit it goes to 2 positions, in the initial carry position and in BI and V position, and this operation control also forms another control input which goes to all of these. Okay. So, now what we have done here is we have taken care of the core of these 4 instructions, AND, OR, add, subtract, and in fact strictly speaking we have actually accounted for not just these 4 instructions, but additional 4 instructions which correspond to their immediate version. So, there is an well, subtract has no subtract immediate, because the constant, if you add a negative constant, you can effectively do subtract immediate. So, effectively that means 7 instructions, AND, OR, add, subtract 4, and then AND immediate, OR immediate, which is ANDI, ORI, and add immediate. Okay, these 7 instructions will all utilize this part of the circuit. Going further, actually there are as far as add and subtract are concerned, there are 2 different types of add instructions, add and add unsigned. So, there is an instruction add and ADD and ADDU. So, now question would be why we have 2 separate instruction add and add u, when we have said that addition can be done with the sign ignored when you are using 2's complement representation. Then what is the purpose of having 2 different instruction? Okay. The reason is that there is something which we have ignored here, is the detection of overflow. Okay, what happens when the number which is coming out as a result here is not within the range of numbers which can be represented. So, when you are adding two very large numbers, the result may be beyond the limit, or you are adding two large negative numbers, still you may exceed the result on the limit on the negative side, or you are subtracting a large negative number from a large positive number, or vice versa, subtract a large positive number from a large negative number. Again the range could be exceeded, and it is here in the in these limits where positive and negative numbers differ, or signed or unsigned numbers differ. Okay. If you are working with signed numbers, your range is from something negative to something positive. Okay. To be more precise, your maximum negative number is minus 2 raised to the power 31, and maximum positive number is 2 raised to the power 31 minus 1. But when you are working with the unsigned number, the range is different, 0 to 2 raised to the power 31, 2 raised to the power 32 minus 1. Okay. So, therefore, detection of overflow is different depending upon whether the numbers are signed or unsigned. So, the process of addition and subtraction remains unchanged, but it is overflow detection which is different, and we will look at it separately. So, effectively this circuit will cater for these instructions, their immediate versions, okay, their unsigned versions. Of course, there is add u and subtract u, and there is also unsigned version of add immediate. So, add I u. So, all these instructions are taken care of by this small unit. Of course, we are not saying that this itself is sufficient to implement the entire instruction. So, the processor has to have other things. There is a register file, there is a program counter, there is a mechanism of getting the instruction from memory, interpreting it, storing the result back, and so on. But this is the key unit which performs the operation, so that we have seen. Okay. So, in to summarize what we have done today is we have looked at 2's complement representation for signed numbers, and seen that it first of all brings a unique representation for 0, which was the problem in other, and secondly it simplifies our mechanism for performing operations. So, circuit is simpler, we can ignore the sign while we are working with it. We also notice that addition and subtraction hardware has a lot of commonality, and since we are either doing addition or subtraction in the processor, okay, we can share the hardware. We have seen that logical functions and or can be easily included in the design of the ALU simply by putting those gates and multiplexes together. Now, one thing which we have left out is of course overflow detection, but secondly comparison is what we have not looked at yet. Okay. So, we would now not today, in the next lecture we will extend the circuit to accommodate instructions like SLT or instructions like BEQ. So, BEQ makes comparison for equality, right. So, we will augment our ALU to do equality check, alright. We will also augment it to do SLT operation, which means comparison for less than and generating a result which is either 0 or 1. Okay. So, these two instructions will be accommodated in the ALU next time.